We will spend some time looking into the influence of demand, that is, consumption from service connection points on a system, and their effect on transient behaviours. Not all systems are as simple as a single pipeline transporting fluid from one location to another. Many systems are more complicated and involve intermediate demand points along a pipeline or throughout a pipe network, the obvious example being potable water distribution networks. As a result, this lesson comes in two parts. The first part introduces you to the fact that the quantity of demand during a single transient event affects surge pressures. And the second part shows you how we model demand in the case study. So let's jump into part one. How does demand affect pressure surge outcomes produced by a transient event, such as a pump start or stop? We start by thinking about three aspects of surge outcomes. First, how close the maximum or minimum heads come to the system's design limits. Secondly, the amplitude of the pressure surge generated. And thirdly, the fact that periods of high demand cause a system to operate with its assets at maximum capacity, meaning higher velocities in the pipe network. When a power failure stops all pumps during maximum peak hour demand, the initial steady-state hydraulic grade lines are likely to be at their lowest levels. The initial hydraulic grade lines will be closer to the minimum head design limit, which is likely to be near ground level. Consequently, a pump stop scenario at maximum demand may generate the lowest heads in the system. In the dead of night in winter, customer demand on the pipe network may be negligible. As a result, initial steady-state hydraulic grade lines are likely to be at their highest levels. Consequently, a pump start or pump stop scenario with low demand may come close to the maximum permissible head. In summary, the absolute values of minimum and maximum transient heads can depend on customer demand. Now shifting our thinking to the amplitude of pressure surges. Remember that the rate of velocity change governs the surge amplitude created. A pump stop scenario with no demand during a winter night will generate a velocity change from the pump's flow rate down to zero. The scale and rate of velocity change will depend solely on the pump's behaviour. Flow and velocity changes in some parts of a reticulation pipe network will be negligible throughout the entire pump stop event. Velocity changes will only occur in pipes carrying pump flow from source to its destination. However, pressure surges propagate throughout the whole system. The scenario will generate surge amplitudes different to other scenarios. Only by transient analysis can you understand if this scenario creates the worst outcomes, and if this is true in some locations and not in others. In comparison, the velocity change created by a pump stop when large customer demands are present may be much less in some or most pipes in the network. In our case study, when the pump stops, flows in some pipes will change from being sourced from the pump to being supplied from the summit tank. Near extremities of the reticulation network, the flow rates and direction will simply continue as they were, heading in the direction of the customers. For several pipes in the system, the continued flow toward customers will mean that their velocity change is only marginal, lowering the rate of velocity change in those pipes, dampening surge amplitudes in their locations. Again, this scenario may or may not be the worst case. Conclusion: when a system contains customer demands, designers need to analyse transient events at various extremes of demand. For example, the relevant scenarios could be power failure to the pump station with a single duty pump running and no demand, and Power failure to the pump station with all duty pumps running and peak hour demand.